My name is Breanna Holmes, and I have worked with Dr. David Majors in the computational chemistry group in the Department of Biochemistry and Chemistry at Mississippi College. This talk is about the conventional strain energy of methyl derivatives of bicyclic systems and individual rings within these systems. What we are doing is calculating the conventional strain energy of bicyclic systems using the S-homodesmotic method. Before I explain what that actually means, I want to talk to you about why we're doing what we're doing. One reason we're doing what we're doing is to investigate ring additivity. That is, we want to see to what degree is the conventional strain energy of the branched portion of a bicyclic system, shown in blue, and the conventional strain energy of the unbranched portion of a system, shown in red, equal to the conventional strain energy of the entire system, shown in purple. Also, we are investigating how branching affects the conventional strain energy of a system. For example, is the unbranched spiro-2,2-pentane's conventional strain energy less than, equal to, or greater than the 1-methyl spiro-2,2-pentane system? What is ring strain? Ring strain affects the relative stability of cycloalkanes. Strain was brought to chemistry as a concept in 1885 by Adolf von Baeyer. He noticed that the smaller the bond angle of a cycloalkane, the higher the ring strain. However, there are other types of strain, such as stretching or compression, Pitzer, which is torsional or bond-eclipsing strain, and the Dunit-Shoemaker strain, which is a non-bonded strain. Not all strain is destabilizing. If you take, for example, cyclopropane and cyclobutane, because of the Baeyer strain or the bond angle strain, you would expect the conventional strain energy of cyclopropane to be much higher than that of cyclobutane. But it's not. It's so close to that of cyclobutane that it's almost within thermodynamic accuracy of plus or minus 1 kcal per mole. So, in order to account for all of the stabilizing and destabilizing forces in a cycloalkane, Cox and Pilcher in 1970 brought to us the concept of conventional strain energy, or CSE. This is the sum of the stabilizing forces and the destabilizing forces of a molecule. Experimentally determining the conventional strain energy of cycloalkanes. We know that straight-chain alkane heat of combustion is about 157.44 kcals per mole for every CH2 present. So, for example, propane would have an entire heat of combustion of 157.44 times 3. We would then compare this with the cyclic version of propane, cyclopropane. And the difference of these two heats of combustion are due to the conventional strain energy of cyclopropane. However, as a group, we are not interested in experimental calculations. We are interested in theoretical calculations. Theoretical calculations of conventional strain energy is quite promising. If you look below, there is a table for the MP2 0-point energy corrected triple zeta calculations of the homodesmotic and hyperhomodesmotic equations for cyclopropane and cyclobutane. You can see that both the homodesmotic and hyperhomodesmotic results for cyclopropane are very close to that of the experimental result for cyclopropane, and the same can be said for cyclobutane. The reason we find CSE calculations so promising is that these results are thermodynamically accurate. because they are within plus or minus 1 kcal per mole. Calculating the conventional strain energy of cycloalkanes. Our group uses the S-homodesmotic model. As you can see, we add together the unstrained ring and ring fragments that yield longer ring fragments to longer ring fragments that yield ring fragments in the true ring to get the unstrained ring that yields the true ring. Equation 1, the energy is 0 because every bond that is broken is remade. Therefore, the energy of equation 2 is the same as the energy of equation 3, which is the conventional strain energy. The value of S determines the length of the fragments. If S is 0, we have an isodesmic reaction. If S is 1, we have a homodesmotic reaction. If S is 2, we have a hyperhomodesmotic reaction. This slide shows examples of the isodesmic, homodesmotic, and hyperhomodesmotic equations for spiro-2,2-pentane. You can see that in the isodesmic equation, the number and types of bonds are conserved. In the homodesmotic equation, it is an isodesmic equation that also conserves the valence environment around each atom. In the hyperhomodesmotic equation, you can see that it is a homodesmotic equation that also conserves the valence environment around each set of 2 bonded atoms. The 7 bicyclic systems being studied in this project are shown here. One of the main goals of this group is to determine to what degree bicyclic alkanes are additive. How we do this is we take each of the 7 molecules shown on the previous slide and calculate their conventional strain energies according to the 4 levels of theory and 2 basis sets shown below. Therefore, each system's branched ring, unbranched ring, and system as a whole has 8 calculations. What we then do is we add the conventional strain energy of the branched ring to the unbranched ring and subtract the conventional strain energy of the system to see how different they are. Shown are the results thus far of this project. Here are the results for all 7 molecules according to the B3 lip triple zeta and the MP2 triple zeta calculations. A few conclusions can be drawn. First is that the isodesmic results are unreliable and are therefore not reported. Also, generally, the conventional strain energy of the overall system increases as 2 rings get closer together. However, there is little difference in that of the 4 systems in which the 2 rings are separated by 1 or 2 carbon bonds, and those are the first 4 listed. 1-methyl, 1-cyclopropyl methyl cyclopropane through 2-methyl bicyclopropyl. Also, the hyperhomodesmotic model yields unreliable results. The hypothesis here is that the ring fragments are so large that they have their own conventional strain energy factors independent from the ring system. Finally, the position of the methyl substitution has very little effect on the conventional strain energy of the system. Clearly, future work would involve doing the necessary calculations to fill in the empty results shown here. The conclusions I spoke about previously are listed here on this slide. This slide concludes my talk. Thank you so much for your time.